Today we discuss open mapping theorem where x and y be Banach spaces and tx to y be a surjective bounded linear operator. Be a surjective bounded linear operator. Then T is an open mapping. Then T be an open mapping. We have to prove that. But before this before this open proof of this open mapping theorem, we also discuss some lemma and some consequent result which is needed here. Okay, let x be a linear space and CD subset of x. Let x be a linear space and CD subset of x. Okay, CD subset of x and let x0 belongs to x and alpha belongs to k and alpha belongs to k. Then C plus D equal to those x plus y such that x belongs to C and y belongs to D. And C difference D equal to x difference y such that x belongs to C, y belongs to D. And alpha C equal to alpha x such that x belongs to C. Now this closed ball or open ball BR x equal to those y belongs to x such that d of xy less than r. Okay, this equal to those y belongs to x such that norm of x difference y less than r. Here BR x closed x means those y such that d of xy less than equal to r equal to y belongs to x such that those of x difference y less than equal to r. Okay, now also we going to another result of this x plus br0 equal to brx. Okay, and also we going to another result t of if t linear then t of t is equal to t of r b1 x0. Okay, and this one equal to r of t b1 x0 if t is linear. Okay, then we now prove one lemma and consequent open mapping theorem. We write this one and now we prove one lemma. This one is an important lemma. Okay, first we write the statement of this lemma. Let x y be Banach spaces. Let x and y be Banach spaces and tx to y be a surjective. Let tx to y be a surjective bounded linear operator. Then the image of unit open ball then the image of unit open wall, that is T of p1x0, is contained an open wall, is contained an open wall b row y0 in y for some row greater than 0. Now we prove this important lemma. This one is typically hard and also long lemma, but we prove first this one, then we're going to this proof of open mapping theorem. Or now we start about it. First we write let r greater than 0. Then by linearity of t, we have what we get, t of b r x0 equal to rt of b1 x0. Okay, next, since t be on 2, we have y equal to union of n belongs to n, t of bn x0. Okay, since y is complete, there exists k belongs to n, such that interior of this is non-empty. Interior of t b k x0 closure not equal to 5. Okay, so let y0 belongs to interior of t b k x0 closure. Now we first claim that 0 belongs to interior of t b k x0 difference y0. Okay, now we claim this one. Now define if y to y. Define if y to y, f of y equal to y minus y0. Clearly f is a f is homeomorphism. Clearly f is homeomorphism. Note that f of t b k x0 closure subset of f of t b k x0 closure. Okay, this implies that this implies that this implies that T of pkx 0 closure minus difference y0 subset of T of pkx 0 difference y0 closure. Okay, now we shows that we erase our portion. We also shows that y0 is an interior point. Y0 is an interior point of T bkx0 difference y0 closure. Then y0 is an interior point. Then y0 is an interior point of this. Y0 is an interior point of this closure. Very good. Y0 is an interior point of tvkx0 closure. This implies that there exists an open set G in Y such that y0 belongs to G subset of tvkx0 closure. This implies that f of y0 belongs to f of G subset of f of t pkx0 closure. This implies that 0 belongs to f of G subset of f of this equal to t bkx0 closure difference y0. This implies that 0 is an interior point of t vkx0 closure difference y0. Okay, we also do first claim. 0 belongs to interior of tpkx0 difference y0. Now we going to second claim. We erase our all portions and also we going to second claim. Okay. Now claim 2. Claim 2 T bkx0 difference y0 subset of T b2kx0. Okay, how we prove this one? To prove so simply, for this let y belongs to tbkx0 difference y0. Then there exists x belongs to bkx0 such that y equal to tx difference y0. One can assume that assume that one can assume that y0 belongs to t b k x 0. Okay, then t x 0 equal to y0 for some x 0 belongs to b k x 0. Okay, then thus y equal to tx minus tx 0 equal to t of x minus x 0. Okay, now note that norm of x less than k. Okay, and norm of x0 also less than k, because this one is belonging to bkx0. Okay, then this implies that norm of x difference x0 less than equal to norm x plus norm x0 less than equal to less than norm of 2k. Okay, this one less than equal to this implies that x difference x0 belongs to b2k x0. This implies that t of x difference x0 equal to y. This belongs to t of b2k x0. This implies that hence we show that this one t k x0 difference y0 subset of t 2k x0. Okay, what a important claim. We've done this one so easily. Now we proceed further. We also erase these portions. Now we're going to claim 3. Claim 3 is one important, and also prove this one. Claim 3. We write claim 3 here. Here b rho y0 subset of tv1x0. That means this one is this proof of lemma. Okay, for some rho greater than 0. First we show that 0 is an interior point of t b k x 0 closure difference y0, and second we show that t b k x 0 difference y0 subset of some image set of some open ball of radius 2k. And also now we show the proof of this lemma. So we claim this one. Now we prove this one. How we prove it? First we let y belongs to b epsilon y0. Okay, this implies that since b epsilon y0 subset of t b epsilon y0 subset of tv1x0 closure, there exists and y1 belongs to tb1x0 such that y difference y1 less than epsilon y2, where y1 equal to tx1, and for x1 belongs to v1x0. Okay, note that y minus y1 belonging to by epsilon y2 0. Okay, hence b epsilon y0 subset of tv1x0 closure. This implies that b epsilon y2 y0 subset of tp half x0 closure. Okay. Now, hence there exists an y2. Hence there exists an y2 belongs to t b half x0 such that such that such that y difference y1 difference y2 less than epsilon y2 square and y2 equal to tx2 for some x2 belongs to b half x0. Okay, then we going to in general y difference y1 difference y2 dot difference yn less than epsilon by 2n with yn equal to txn for some xn belongs to b1 by 2 to the power n minus 1 x0. Okay, then then what we get, then we get Sn equal to, we erase these portions. Okay, we erase this portion. Then what we get, we get define Sn equal to x1 x2 dot xn for n belongs to natural number and hence Sn plus 1 difference Sn equal to norm of xn plus 1 less than 1 by 2 to the power n. N belongs to natural number. It follows that Sn is in Banach space X. It follows that Sn is in Banach space X. Then limit n tending to infinity Sn equal to X belongs to capital X. Okay. Now by continuity of t t of Sn converges to tx, and also by linearity of t we have norm of y difference y1 y2 dot yn equal to norm of y difference t of x1 t of x2 dot t of xn equal to y my difference x1 x2 dot xn. Okay, then this equal to y difference t of Sn less than epsilon by 2 to the power n for all n belongs to capital N. Hence t of Sn tends to y. Then by uniqueness of limit of t of Sn we get we get tx equal to y. Okay. Then since Sn less than equal to norm of x1, norm of x2, norm of xn less than half 1 plus half square 1 by 2 to the power n minus 1 equal to 2. Okay, which gives that which gives that which gives that which gives that norm of x equal to limit n tending to infinity norm of Sn less than equal to 2 less than 3. Thus, thus what we get thus we get thus we get x belongs to B3x0. This implies that y equal to tx belongs to tb3x0. We see that we see that we see that y belongs to b epsilon y0 for epsilon greater than 0. This implies that y belongs to t of b3x0. Thus b epsilon y0 subset of t of b3x0 for epsilon greater than 0. That is epsilon equal to rho equal to epsilon y3 greater than 0, then p rho y0 subset of t of p rho y0 equal to b epsilon y3 y0 subset of t of b1 x0. Okay, for rho greater than 0. We prove our claim. So we prove this lemma and now we proceed open mapping theorem. Okay, we proceed open mapping theorem uh, in next class. We just write the statement of open mapping theorem. Okay, we just write the statement of open mapping theorem, then we proceed it next in next class. Statement of open mapping theorem. Open mapping theorem. Let xy be Banach spaces. Let xy be Banach spaces. Banach spaces and tx to y and tx to y be a surjective bounded linear operator. Be a surjective bounded linear operator. Then T is an open mapping. Then T is an open mapping. How we prove it? We prove it in next class. We just write this statement of this open mapping theorem. xy be Banach space and then T is a surjective bounded linear operator. Then T is an open mapping. We also see today this lemma. This lemma is satisfying those conditions of open mapping theorem, and lemma says that any image of open ball of X, any image of open ball of X is contained an image set of open ball, an image set of open ball. Okay, that means any open ball of Y is contained in image set of open ball. Any open ball in Y is contained in an image set of open ball. Okay, so today we stop here.